morning. We looked at a few parameters relating to these chemical reactions, and what did we take a look at? We looked at the burning velocity SU, also talked in terms of a flame speed which takes care of the burning velocity when the observer is on the ground. Burning velocity is when the observer is on the flame, that is with respect to the flame. We derived an expression for the flame thickness. We said, well, the flame thickness is very small. Then we also looked at the pressure drop across a flame, and we found that it was almost negligibly small. And then we told maybe it's time for us to examine the question of maybe the quenching thickness or a quenching distance, a characteristic length scale for quenching. Why do we want to take a look at the quenching distance? Let us go back to our problem. We had a gaseous mixture and maybe an explosive gas mixture. In this explosive gas mixture, we release some energy in a small volume. We said if this volume or kernel, which we called as ignition kernel, is such that it is not able to propagate the flame, that means heat the adjacent layer and propagate a flame as it were, and it sort of collapses, that means it sort of extinguishes or it quenches, then a flame is not possible. It is essential to have the flame kernel of a minimum size such that it is capable of propagating a flame across. Therefore, we wanted to study this quenching distance. Let us have a simple format in which we study it. Let us consider, let us say, a pipe. In this pipe, let us say the pipe is of diameter d. Let us say these are the walls of the pipe. In this particular pipe, I have a flame which is travelling. This is the flame which is travelling. I assume it to be planar, and let us say it travels, as you know, at a speed SU. And we said we will look at the problem with the flame stationary, that is in the plane of reference of the flame, and therefore, we said, well, I can have the tube as it is, I have the flame. Now, I put a particular thickness of the flame which we calculated in the last class as TF, so much millimeter. We found it is quite thin, of the order of a millimeter. Well, this is the flame as it were, and what does the flame do? It to the wall, it allows some heat to get conducted to the wall. In other words, some heat gets lost from the flame to the wall, because if I were to put the wall over here, the wall is somewhat at a low temperature, maybe of the order of the initial temperature itself, and from this region of hot gases, which is the flame, some heat gets lost to the wall. But along with the heat loss, some heat is also getting regenerated or created within the flame, and therefore, there is a balance between the heat which is generated by the flame and heat which is getting lost. If the heat lost from this zone of flame is greater than the heat which is generated, well, the flame will collapse, and I can calculate a critical thickness or a thickness d for which maybe I have quenching of the flame, and that is what I want to work out. Therefore, let us first determine what is the heat loss, what is the heat generated, and then let us try to arrive at a diameter which corresponds to the quenching. That means, the condition at which the heat lost from the flame is equal to or greater than the heat which is generated by the flame itself. Therefore, let us write the expression. We say, well, the heat lost from the flame zone to the wall, well, the thickness is T. Let us initially assume, well, the diameter is d, as I have put over here. Well, the perimeter is pi d into the area of contact between the flame and the wall is equal to the perimeter into the thickness, which is equal to pi d into Tf, which is the area, and H into, let us presume that maybe the temperature distribution is such that the walls are cool, the thing is hot here. Therefore, I say, well, the maximum temperature in the flame is the burnt gas temperature, the wall is Tb, I assume a linear gradient. Therefore, I have the thermal conductivity into the burnt gas temperature minus the wall temperature divided by d by 2, which is the radius, and this is the gradient. I linearize it. After all, I am interested in the trends, I am looking at this. Well, this is the heat lost from the flame to the wall. What is the heat generated by the flame? Let us say heat generated. Well, we know this, we have been writing this on and off. We say that the rate of reaction is omega, so much moles per cc second, into the heat, which is so much kilojoule per mole, into the volume, which I can also write as equal to, which we can also write so much, let us say joule per second or kilojoule per second, this is joule per second or watts over here. Therefore, I can also write the heat generated as, I am sitting on the flame, therefore, I see the mass flux rho u and SU coming, and therefore, what is the mass which is associated now? The cross sectional area, this is flux into the area which is pi by 4 d square. Therefore, this multiplied by Cp into Tb minus Tu, which is the unburned gas temperature, is the heat which gets generated by the flame. But after all, you have this stationary, therefore, in this frame of reference, I have SU coming here, rho u SU coming, this is the mass, the temperature increases from Ti to Tb, therefore, this is the heat which gets generated over here. Therefore, for the condition in which heat loss has to be less or heat loss has to be greater or more than the heat generated, that is the condition under which quenching takes place, that is the heat loss is greater. I have the condition, well, pi d into Tf, this is the area, into the thermal conductivity, into Tb minus Tw, that is the wall temperature, divided by d by 2, must be greater than or equal to the value of heat generated, which is equal to rho u Su into pi by 4 into d square into I get Cp into Tb minus Tu. Well, I want to find out the critical condition, and the critical condition is, well, it must be equal to it, and when does it become equal? When the diameter becomes equal to the quenching thickness, that is, it is just equal, that is, the heat loss is just equal to the heat generated. Well, in that condition, I say d is equal to d quenching thickness, and therefore, what I put here? Well, I put here, this is d, this should have been small d over here, because that is the diameter I am considering. Therefore, I have small d over here, and therefore, what is the condition I get? I get dq over here, I get dq over here, I get dq over here, or rather I have to solve this particular expression in which I want to determine the value of the quenching thickness. Immediately I find, well, for this particular expression, when I put dq, this becomes equal to sign, because I am considering the critical condition. Therefore, if I were to solve this, well, I find dq and dq cancels over here. I also find the value of pi and pi gets cancelled, and what is left is I have the value of Tf here, I have thermal conductivity here. Well, I also find Tb minus Tw, and I have Tb minus Tu here. See, initially the temperature at the wall is going to be something like the initial temperature or the unburned gas temperature. I can approximate Tw as equal to Tu, and therefore, I can cancel these two terms. Therefore, under this condition, that maybe for Q it becomes the equal to sign, what is it I get? I get K into Tf, and this is multiplied by 2, because this is dq by 2 is equal to, I get rho u into Su into divided by 8 over here, divided by 4 over here, into dq square into Cp. Therefore, from this expression I immediately see, well, I have accounted for all the terms here except for those which are cancelled. Therefore, I get dq square divided by Tf is equal to dq square divided by Tf is equal to 8k divided by rho u Su divided by Cp. This is the expression for the quenching thickness square divided by the flame thickness. This is what I get. But if you go back to last class and see what was the value of Tf, we said, well, the thickness we derived for the flame thickness, which we said is small, was equal to the thermal diffusivity divided by the flame speed, which we could also write as K divided by thermal diffusivity was K divided by rho Cp or rho u Cp into Su, or therefore, I can write this. I have K divided by rho u into Cp is alpha divided by this. Well, this becomes equal to 8 into Tf, and therefore, this particular expression now becomes dq, let me use this part, dq square divided by Tf square is equal to 8, or rather dq by Tf is equal to root 8. Well, we have succeeded in getting an expression for the quenching length scale or the quenching distance, and we find that the quenching thickness is of the order of something like 3, but in practice it is an order of magnitude greater, maybe of the order of 8 to 10 or 8 to 12, let us say, is the value in practice. Mind you, we have made very simplifying assumptions, and that is why we get a number, but it is representative. Therefore, we find, well, the value of quenching thickness is greater than the film thickness, and mind you, this quenching thickness is a very, very important parameter from the safety point of view. We will shortly take a look at it, but before that, let me go back and look at this expression again, or let us take a look at this expression. I can write this expression again as equal to rho u Su Cp into dq, let me write it here, rho u into Su into Cp into dq divided by, I bring k down over here, and this I write as equal to, that means I take here, therefore, I get 8 into Tf by dq but just now we told, see, dq by Tf is a constant, we arrived at 8, we said it is equal to this. I can as well write dq by Tf is something like a constant which is of the order of, let us say, 10 or so. Therefore, well, dq by Tf, I have this value, therefore, I can say this particular parameter which contains the quenching distance is a constant k. And what is this representative? Let's take a moment off and take an expression this. At the bottom I have thermal conductivity. If I were to multiply thermal conductivity by something like Tb minus T ambient, well, and I also bring dq from top at the denominator over here, dq, such that I eliminate this, well, it gives the conduction heat transfer, and if I multiply by the numerator also by Tb minus Tw, and therefore, this I have brought down, I have rho u Cp into Tb minus Tw in the numerator, which is something like a convection, that is, the flame is moving or the burning speed is Su, this is the convection what you have, this is the conduction what you have, and therefore, we are talking of something like a convection heat transfer divided by conduction heat transfer, which gives me a value of C, and this convection heat transfer divided by conduction heat transfer is known as Pecklet number. Therefore, we say for quenching to take place, Pecklet number has a particular value, and I can use the Pecklet number to be able to determine by quenching thickness. But for us, well, the expression dq by Tf is a constant, and this constant is of the order of 10, is sort of something which is very representative. Why is quenching thickness so important? Not only can I get into my problem which I set out to do to be able to get my ignition energies, which we will shortly do, I just want to spend a moment or two. Mind you, when we were in our school days, we heard of something known as a Devi's safety lamp. What is this Devi's safety lamp? Let's quickly review this. See, when a miner goes into some, let us say, a mine, and the mine contains some explosive gases, deep down, mines, you have hydrocarbon, coal, generate some methane gas, you have air available, I can form an explosive gas. And a miner, in the dark space, he needs some light, he carries a light source, and maybe the light source could be a hurricane lantern or a lamp. And therefore, let us say he carries a lamp, I just illustrated by a candle. Therefore, you have a candle here which burns. But then if he is going to carry a heat source which is as good as an ignition source, the mine will catch fire and it will explode. Therefore, what was suggested by Devi in early something more than 100 years back is maybe you encase it by something like a sieve or a sort of a shield which has fine holes in it. You know, the size of these holes, that means I have something like a sieve and you have holes in it. Let that, if the diameter of the holes is less than the quenching thickness, what is going to happen? Well, a flame cannot pass through these holes because the flame will quench the moment it sees a smaller hole, it cannot pass through because the heat loss takes place, and therefore, when you have a lamp which is surrounded by this sieve whose dimensions, whose openings are of the order, whose openings are less than the quenching thickness, well, a flame cannot propagate out and it is something like a safety device. This is what is the principle of a safety lamp. Therefore, we say, well, Devi's safety lamp uses the quenching distance or a quenching diameter to make it foolproof. It cannot explode the gas, and even if the gas comes over here, you know, after all through the holes it will come over here, it can burn over here, but it cannot go and cause a catastrophic explosion in the mine. In fact, this quenching thickness is also used, like we have the Olympic torches these days, you know, and what happens, you have the Olympic torch which has a huge flame, and you know, you have to carry it, maybe you want to carry it in an aircraft, you want to carry it at different places, and you know, as a shield, if I can put something like a sieve whose dimensions are less than the quenching thickness of the gas which I am considering, suppose a medium is somewhat explosive, then you know, I am safe, you know, I will not really go and make the ambient catch fire, and this is how a quenching thickness is applicable. Having said that, let us get back to our problem. We wanted to use the quenching thickness to be able to model the ignition. Let us do the ignition problem. You know, I think we should also have a feel for numbers. Let us put down the type of quenching thicknesses, what are there for a few gases, such that we know the order of magnitude. For methane air, the quenching thickness dq is around 2.5 millimeters. When I talk of propane air, the quenching thickness is of the order of 2 millimeters. When I talk of butane air, again it is of the same order, it is of the order of 3.4 mm. Therefore, we can say for the hydrocarbon gases which are essentially saturated gases in air mixtures, the quenching distance is between 2 and 3 mm. When we go to acetylene, C2H2 and air, which we found, you know, has a much higher flame speed than these had around 0.5, this had almost around 1.7 or 1.8 meters per second. The quenching thickness is very much smaller, of the order of 0.8 mm, and the hydrogen air has a value around 0.6 mm. Therefore, you find, well, I can readily make a sieve of these dimensions and protect my gas over here, protect maybe the gas from explosions using these safety distances, while for hydrogen air, well, I need to have pores which are much smaller, and maybe you use some particular materials, some fabricated using powder metallurgy to give these small pores and still use it as a safety device. Yeah, with this background, let us come back to our ignition problem. Well, we see, well, I need an ignition kernel whose dimension must be greater than the quenching thickness. Let us come back, let us illustrate this problem again. I deposit some energy over here, maybe this is the volume in which, this is the place where I have the explosive gas mixture. I deposit the gas in this particular volume, and we say, well, the dimensions of this must be such that, let us say, mean diameter of this particular volume must be greater or equal to the quenching diameter for it not to collapse because of the cooling effect from the ambient, but it must be able to propagate a flame over here. This is the minimum thickness of the ignition kernel. It must at least be the quenching diameter such that it does not collapse when it is cooled from outside, and therefore, we tell ourselves, but what should the igniter be doing? What should the spark be doing? The spark should be able to ignite the next layer of gas, the heat which is being transferred out, and not only the heat which is being transferred out, maybe the concentration of active species which are being transferred out to the immediate next layer, which I show by this particular shaded portion over here, it is the next portion, must get ignited by this kernel whose diameter is, let us say, dq. And what must be this thickness? Well, it must be the order of thickness of the flame. Therefore, it must be able to ignite a segment, or let us say an annular spherical volume of thickness Tf. We know, well, Tf is small, well, Tf is of the order of 0.1 mm or so. This dq could be of the order of, as we said, around 2 mm, maybe if it is hydrogen it is small, but anyway it has to ignite the next one, and what will happen? This ignited gas will again ignite the next gas, and so on, and this is how a flame will propagate out. Therefore, what is the mass of gas which the kernel must ignite? Well, the volume of this spherical shell which surrounds it is equal to pi by 4. No, we are talking of a spherical shell. The surface area of this sphere here is equal to 4 pi r squared, that is equal to pi into dq square, because we say, well, it is of the order of quenching thickness. Well, Tf is small, therefore, the volume of the spherical shell is equal to pi dq square into Tf. The mass of the spherical shell is equal to pi into dq square into Tf into the unburned gas which is originally there in this, and this is the mass of the spherical shell. You multiply by Cp, which is the thermal mass of this spherical shell over here, shown in color over here. And what must the gas do? It must get sufficient heat such that it is able to increase its temperature from the initial value to say about the burned gas temperature, and therefore, this must be equal to Tb minus Tu, and this will be the energy required for ignition. That means, for ignition I need to form a particular kernel or a volume whose dimension is of the order of the quenching thickness, and the heat from this, or the heat and concentration from this, should be able to form a flame of thickness Tf, and such that propagation continues from layer to layer over here. Therefore, the energy required is the energy content within this kernel, and the energy content should be equal to pi d squared Tf into rho u. It is not the energy content within this which is important. The energy content must be able to ignite the gases whose thickness is Tf, and therefore, we say, well, the ignition energy is so much, and this we call as equal to the minimum what is required, minimum ignition energy, or simply MIE. See, we must remember this, because see, we are interested in igniting the neighboring thickness of a distance equal to Tf using this particular kernel. Therefore, well, we write the expression, well, minimum ignition energy, let us say in joules, is equal to, now I say pi dq square. Why is it minimum? Because I am considering the minimum thickness. Any diameter greater than this is going to ignite. Therefore, it is minimum ignition energy in joules, pi dq square into Tf into rho u into Cp into Tb minus Tu. Well, I can simplify this expression and write this as equal to, well, I know, we just now said dq by Tf has a magnitude, is a constant value, is about an order of magnitude greater. We found from theory it is equal to under root 8. Therefore, I can say dq or Tf is equal to dq by C, and I can rewrite this expression by MIE is equal to pi dq. I have Tf is equal to, I substitute that as equal to dq by c, therefore, it becomes dq cube by capital constant over here into I have rho u into Cp, I take Tu outside and I get, if I take let us say Tu outside, I get Tb by Tu minus 1. Now, if I look at this expression, well, the burn gas temperature is definitely higher than Tu, maybe it is of the order of 4 or so, therefore, I say this is of the order of 3, which is anyway the burn gas temperature is very much higher, and therefore, I can neglect 1 over here, I just take the value as a high value over here. The initial gas temperature is specified, the initial gas density is specified, I know the specific heat of the gases, which is anyway a constant for a given gas mixture. Therefore, I say the minimum ignition energy goes as dq cube, that is as the quenching distance cubed. And this has been found on the basis of experiments. Yes, indeed, minimum ignition energy goes as dq cubed, and this is the logic we use, and therefore, we find, well, for ignition I now am in a position to calculate what is the energy required for ignition. And if we use this and calculate the ignition energy, we find that for hydrocarbon gases, well, the ignition energy is typically of the order of something like 0.2 to 0.3 millijoules. You know, for let us say maybe propane air, butane air, maybe methane air, it is of this order. If I consider maybe the hydrogen air mixtures, it is much lower, it is of the order of 0.018 millijoules, that means 10 to the power minus 3 joules. And if I consider acetylene air, and we found, you know, acetylene was always a substance which had the 3 double bonds, and it was a positive heat of formation, something which is unstable or which is not very stable, a powerful explosive, the energy is of the same order, around 0.017 millijoules or so. Therefore, we find, well, the order of magnitude is 0.2 millijoules, and we use the theory to be able to do this. Therefore, right now we are in a position to find out under what condition an explosive can be ignited, and once it is ignited, well, heat release takes place and a blast wave is formed, or some pressure waves are formed. Well, you know, we talk in terms of ignition, we talked in terms of maybe quenching thicknesses, but are there some gases which cannot really be ignited? You know, let us think of this. We now know how to do an ignition problem or to model an ignition problem, but are there some gases which really cannot be ignited? Let us consider the following situation. We say a gas mixture. When we say a gas mixture, let us take an example. I have methane and air as a mixture. Well, the mixture could be stoichiometric, that is equivalence ratio is equal to 1. Well, it could be fuel lean mixture, it could have so much of air and very little of fuel, it could also be fuel rich. You know, all these things are possible. So, also maybe a solid substance or a compound which contains maybe a carbon, hydrogen and oxygen could be either fuel lean or fuel rich, and we have seen all these things earlier. But is it possible to say, well, on a scale like this, maybe on a straight line like this, well, I say, well, this is my stoichiometric composition phi is equal to 1. To the left of it, I have fuel lean mixtures. On the right of it, I have phi greater than 1, that means my thing is I am representing fuel by air over here. I say I have fuel rich conditions over here. You know, if I keep on decreasing the quantity of fuel such that the quantity of fuel in the fuel lean mixture becomes very negligibly small, we know, well, it is so small that even if it reacts, the amount of energy which it liberates is so small that the temperature rise is insignificant and it cannot support a chemical reaction, and therefore, I can sort of hypothesize, or I can sort of say that maybe for mixtures which are terribly fuel lean, I cannot really form a mixture which can ignite and in which a flame can propagate under steady conditions. So also when the fuel becomes extremely rich, that means I have almost all fuel and almost no air, that is I am just talking in terms of maybe thinking of the problem or putting our mind model into the problem. Maybe when the fuel becomes so rich, that means the value of phi is so large, that means over here it just cannot ignite, the amount of reaction is so small that the temperature is small. Therefore, in practice I can think of maybe under fuel lean conditions there must be a limit below which something cannot burn. Under fuel rich conditions I must have a limit above which something cannot burn, and these are known as limits of flammability. In practice, well, these things are observed, and how do you model it? See, we talked in terms of chain initiation reactions, chain termination reactions. In these mixtures, the chain initiations are so small that I cannot have sufficient chains being formed, and the chain termination takes over and I have the limits of flammability. Therefore, we say, well, a gas mixture can be ignited or it can propagate a flame only if it is within from here to here, that is within limits of flammability. You know, this is a useful safety parameter. We will see this and how to calculate it out. Therefore, for all gaseous mixtures, we have maybe a lower limit, that means lean limit, you have upper limit for fuel rich conditions, and these we call as, let us put it down, we call it as lower limit of flammability and it is denoted by L, and you also have, that is lower limit of flammability corresponds to the lean conditions, that is the lean limit, and you also have the upper limit of flammability, that is corresponding to the rich conditions, which I call as U upper, which corresponds to the rich conditions. Therefore, in practice I have two limits corresponding to the lean limit of flammability and the rich limit of flammability, namely L and U. And how do we specify them? See, we could specify them either by the equivalence ratio, what we said phi is equal to 1 is stoichiometry, when phi is less than 1, well, very small I have the lean limit, when phi is very much larger I have this. But what we do in practice is we specify them in terms of percentage volume of fuel in a given volume of the mixture. Namely, percentage volume by volume is how the limits of flammability are expressed as. Let us do this, let us spend a minute or two, try to find out how we get the limits of flammability, then maybe we will take a look at some of the limits of flammability as has been determined in literature. Therefore, we say, well, now I am interested in maybe percentage volume of fuel in a given volume of mixture, and then, well, I want to first put down what is the heat which gets generated. We say, well, there is a condition like stoichiometry over here, which corresponds to phi is equal to 1, and therefore, when I do an experiment, we saw, well, the maximum heat release happens at stoichiometry because completely burnt products of combustion are formed, and if I find out what is the heat generated in terms of kilojoules per meter cubed of the mixture or per kilogram of the total mixture, what is it we said? Well, the mass of the mixture or volume of the mixture increases over here, even though the heat of reaction remains the same. Therefore, the heat rapidly drops off when in the lean conditions. In the rich conditions, I do not have sufficient air to burn, and therefore, the heat drops off over here. Therefore, this is the type of signature what I get for heat release, let us say QC dot so much kilojoules per meter cube, this is the type of equation what I get, or this is the type of curve what I get. If I have to convert it into the temperature plot, what is it I will get? Well, the temperature is a maximum for slightly not stoichiometric conditions where heat is maximum, but slightly a condition which is somewhat, let us say, fuel rich. Let us put it down, this is the fuel rich side over here, because what happens is many of these fuels have slightly compared to finished products of combustion high somewhat lower specific heat, and therefore, I will have a temperature distribution which is something like this. Therefore, from this is the type of temperature what I get, this is the type of heat release what I get, Q dot C over here. And if my temperature and my heat release is less than some value, let us say at this condition of heat release, for which let us say that the temperature curve, I extrapolate this curve something over here, this is the type of temperature curve I have. Maybe at this particular value I get the heat release is so much for which the temperature is so small that below this the mixture cannot really propagate a steady flame. Well, I say L is over here, in this case I do not get a flammable mixture. So, also when I look at the other side, maybe I am taking at a mixture over here. Beyond this, the mixture is such that it cannot really propagate a flame because the heat release is so small and the temperature is so small that it cannot really propagate a flame. This corresponds to the U, this corresponds to the L, and this is how we look at it. In practice, for most of the hydrocarbon mixtures, the heat is something like 50 kilojoule per mole of the mixture and a temperature of around, let us say 1500 Kelvin is what decides the lower limit, whereas for hydrogen the values are different. It is of the order of something like 20 kilojoule per mole of the mixture, temperature around 800 Kelvin is what decides the limit. These things come from, as I said, from chain branching and chain termination reactions, which really say what is the type of leanness to use, what is the type of richness to use. But L and U are very strong parameters, because if I have, let us say, an explosive gas mixture and it could explode, maybe I could sort of inert it and make it weak such that it is in this region and I am able to handle an explosive safely. And this is an important parameter, therefore, we say L and U are the lean limit of flammability and U is the upper limit of flammability, and it is specified in percentage volume of fuel divided by the volume of the mixture. It is not only possible to have the lean and rich limits of mixture only for the volume in volume, but also maybe as you reduce the pressure of the mixture, like what is it we are doing? Let us consider this simple thought experiment before we examine some values. If I have a volume of the mixture, given volume of an explosive, and let us say it is a vapor air mixture or a gas air mixture, I keep on reducing this pressure. If I reduce this pressure, the concentration of the moles in this gas, that means concentration is N over V, the number of moles in this particular gas will keep decreasing, and if the number of moles of the gas are so small such that it cannot react further, well, I cannot really have a chemical reaction takes place, and this will again correspond to the low pressure limit or corresponding to the lower limit of flammability, and therefore, I can also have lower limit of flammability coming from low pressure of the mixture, and with this we call as the low pressure limit of flammability. Therefore, whenever we have these explosive gases which are formed under subatmospheric pressures, low subatmospheric pressures, well, they may not be able to propagate a flame. Now, we have seen from the point of view of concentration, that is volume by volume, maybe in terms of pressure, what should be the effect of temperature? Can we just presume something? Well, I tell myself, well, temperature, if I have very low temperatures, what is going to happen? Well, the rate of a reaction will be terribly affected, because not much of the heat of the reaction goes into increasing the temperature to the value of the standard conditions, that is 25 degrees centigrade, and therefore, heat may not really be available. And if under standard conditions, let us say at 25 degrees centigrade, well, this is my stoichiometry, phi is equal to 1, this is my percentage volume by volume, this is my scale over here. Well, this is my limit calculated at 25 degrees centigrade, low pressure low lean limit, that is L. I have rich limit U, which is at 25 degrees centigrade over here. Well, if I were to plot on this, maybe at a low temperature of, let us say, -5 or let us say 0 degrees centigrade, well, some heat has to go, and therefore, the lean limit will move up. That means, it will come to this, it will move in this particular direction. Well, the upper limit will come down, it moves over here at temperatures less than 25 degrees centigrade. If the temperature were higher than 25 degrees centigrade, what is going to happen? Well, using the same argument, I can tell, well, if the temperature is going to be higher than 25 degrees, I have more enthalpy in the gases that is going to come as product gases. Therefore, the lean limit moves, becomes even more leaner. This is at a temperature greater than 25 degrees centigrade, and if the upper limit also moves outward over here. Well, let's examine some of these results for some gases and look at the expressions in the slides which I show now. Well, in this particular slide, you see the limits of flammability. It is given by percentage volume in a given volume, and on the y axis I show the minimum ignition energy. Why is it we show the minimum ignition energy? Well, if something is not flammable, the minimum ignition energy tends to a very large numbers, that is infinity. Therefore, at the limits of flammability, the minimum ignition energy is infinity, and therefore, I have U, that is a line over here, which is a very large ignition energy. I have U over here, that is the upper limit of flammability, wherein it is very large, and therefore, I have something like a U-shaped curve coming over here, and these U-shaped curves are shown in a plot of minimum ignition energy versus the fuel percentage volume in a given volume of mixture. Therefore, you find that for hydrogen air mixture, it varies between something like 4 percentage volume of hydrogen in hydrogen air mixture, and it goes right up to something like maybe over here something like almost 70 or so over here at the rich limit of flammability. If I consider something like methane air, if I look at methane air, well, this is the upper limit of flammability, it is around 12%. If I consider the lower limit, it is over here, it is of the order of something like 3% or so. This is the curve over here for methane air. If I take a look at propane air, well, this is the limit over here, lean limit of flammability of the order of something like 2% propane in propane air mixture, and if I go to the rich, well, it is somewhere over here. Therefore, what we observe is for different fuel air mixtures, we get these U type of curves, and the lean limit of flammability is here, rich limit of flammability is here, lean, rich, lean for hydrogen by the continuous line over here and here. And if we can operate the system within the lean limit or outside the rich limit, maybe for the particular gas mixture, well, there is no danger of an explosion, there is no chemical reaction taking place, but if we are within the limits, we must be careful. But we do get another message from this particular curve, and what is that message what we get? We find that at the lean conditions, whether it is methane air, propane air or hydrogen air, we are talking of energies which are almost comparable, which are quite high now. And we find, well, hydrogen, we always have a feeling it is a dangerous gas, but we find the limit of flammability of lower limit is around 4, and if you look at maybe propane air or if you took kerosene vapor, it is almost around the same value, and therefore, and whenever we have spills taking place, you cannot get we get only lean mixtures which are being formed, and therefore, from these curves we get a feeling that maybe hydrogen air mixtures which are formed by leaks are not that dangerous after all. It is as dangerous as any other gas which comes over here. Well, having looked at the lean and rich limits, let us go to the next one. This is where I said when the temperature is such that the temperature is higher than 25 degrees centigrade, I have more of the energy which is available. Therefore, the sensible heat which is higher is C into T minus 25, this is the energy available. More than this, C is the specific heat, T is greater than this, and therefore, since more energy is liberated by the gases, well, the lean limit at temperature T should be less than the limit at 25 degrees centigrade. Therefore, if I have to convert it, I can say, well, LT by L25 should be equal to, or LT is equal to L25 minus some particular value corresponding to this. I put the standard heat over here, I get C divided by the limit at 25 degrees into the heat of combustion, and you sort of say, well, it must therefore have a dependence of LT by L25 is equal to 1 minus the specific heat divided by the heat content at the standard condition into T minus 25, and if I do an experiment, I will find that LT by L25, that is the lean limit at a temperature T which is higher than 25 should be smaller, and the value is 1 minus 0.0072 into T minus 25. If the temperature is going to be lower, well, this becomes negative, this becomes positive, and the temperature limit increases as we discussed earlier. Similarly, the upper limit at any temperature corresponding to the standard temperature of 25 degrees is also given by a similar expression, but in this case when the temperature increases, the upper limit goes to the right, that means it becomes higher value. Well, these are about the limits of flammability, but in many cases I want to qualify this by a particular explanation on the board. We find that maybe when we have the cooking gas at home, it contains not a single gas, it contains, let us say, butane, lot of butane, C4H10. It also contains some propane, C3H8. Therefore, it is instructive to find out what will be the type of flammability limits for mixture of gases with air. Therefore, when I talk of mixture of gases with air, it becomes difficult, because if the gases are similar structure, well, it is possible to use empirical expressions, but in which case I need the moles of this gas and do this. But a general expression which is due to Lee Chatelier, he proposed that it follows a harmonic mean, like for instance, I have F1 of this fraction of volume of this gas, I have F2 of this. If the lean limit in butane air is, let us say, L1, if the lean limit in propane air is L2, well, for this mixture of gases, the limit for this mixture is equal to 1 over, I get F1 by L1 plus F2 by L2. And this is what I show in the slide over here. All what I say is, when I have a mixture of gases which contains maybe similar structure of gases, I have fraction F1, F2, F1 corresponding to gas 1, F2 corresponding to the combustible gas 2, and so on. I have F1 corresponding to nth combustible gas, and the lean limit of gas 1 is L1, the lean limit of gas is L2, and so on up to Ln. The limit for the mixture is given by the Lee Chatelier's rule, which is L is equal to 1 over F1 plus F2 and so on up to Fn. And this is how we calculate the flammability limits, and using the flammability limits, well, I can find out, I can solve problems for maybe the conditions under which a particular gas can explode or will not explode. I can also find out the condition under which maybe a gas, if I have, is, let us say, an explosive. I do not want it to explode, maybe how much of the inert substance I add to it, such that I reduce the limit, I reduce the concentration of the gases to be less than the lean limit of flammability. See, in practice, the lean limit of flammability is more stronger. That means it is something which is an important parameter compared to U, because what happens is, whenever some leak happens in practice, I cannot really form a very rich mixture unless it is a very copious leak, but in general we always talk in terms of small leaks, and therefore the lean limit of flammability is an important parameter which we need to consider. Well, these are about lean limits of flammability. Let's take a look at the last slide over here, in which I talk in terms of the flammability limits of volatile fuels. There is one problem I must tell you. See, if I look at this plot, I show temperature here and I show something like percentage volume by volume here. What is this? It is a little confusing, but let us try to analyze why this particular figure and what it means. I go back to the board. Well, I consider, let us say, petrol, which is available in the market as a volatile fuel, or I say kerosene, which is available. When I have, let us say, a can of petrol which is available, and let us say I increase the temperature of kerosene, what is going to happen? Well, on a cold day, the amount of vapor of kerosene is small, which is getting out over here. If the temperature is higher, I have more of the vapor over here. Therefore, the amount of the concentration of vapor which I can form, kerosene vapor, which I can mix with air, is higher when the temperature of the volatile liquid is higher. Therefore, whenever I consider something like a volatile liquid, the temperature of the volatile liquid will tell me what is the type of the mixture which I can form in the air above it. And if I form a mixture which is flammable, well, at this temperature to store petrol or to store kerosene is going to be difficult. Therefore, if I have an axis which is temperature, and on this plot on the y axis, now I say percentage volume of the vapor of this particular volatile liquid divided by the vapor of the mixture which can be formed. Now, over here I can say, as temperature increases, we say, yes, we saw that the limit of flammability decreases, L. We also saw, maybe in the rich limit, let's erase this top part over here. We saw, well, the U increases with limit of flammability. We also know, as the temperature of the volatile liquid increases, its vapor pressure increases. This is the vapor pressure curve. Therefore, where the vapor pressure, that means I form vapor as the temperature of the volatile liquid increases. At this confluence, that is the intersection of the vapor pressure curve and the L curve corresponding to this, what happens? I generate sufficient vapor which is just at the lean limit of flammability, and if I can increase the temperature just above it, I have sufficient vapor which forms mixture which is above the limit of flammability, and therefore, this corresponds to the temperature, that is the minimum temperature of the volatile liquid at which a flammable limit can be formed, and this temperature is what we call as the flash point temperature. In other words, when we talk in terms of volatile liquids like let us say petrol, kerosene or other substances, we talk in terms of a flash point temperature at which sufficient vapor is formed above the liquid, which when mixed with air forms a limit mixture corresponding to the lean limit L. But what happens? Let's again put this diagram here. I have maybe kerosene or petrol over here. I form a mixture over here which is, let's say, lean limit, and supposing I put a matchstick over here, it immediately burns and the mixture is finished. It just flashes into vapor and then the vapor gets consumed, and that is why it is known as flash point. That means the amount of vapor is not still sufficient to continually keep the fire on. That means I still require more copious amount of vapor to be able to keep the fire on, and if I have more copious, that is still higher temperature, well, I call as a fire point temperature. Therefore, this question of maybe the flash point temperature and fire point temperatures are very useful safety parameters with how to deal with liquids. In this slide, I show the temperature of the volatile liquid as T degree centigrade. I show the percentage volume of the fuel vapor divided by the volume of the mixture over here. I show the value of L decreasing with increase in temperature. I also show the rich flammability limit U increasing with temperature. This is the vapor pressure curve over here. You find, well, at the intersection of the vapor pressure curve and this and the lean flammability limit, I get the flash point temperature. If I want a fire point temperature, the temperature needs to be much higher, and if I increase the temperature further, maybe as we saw earlier, the critical temperature or auto ignition temperature at which self ignition takes place, and this is how we categorize the safety aspects of a volatile liquid. And this is categorized in terms of flash point temperature, in terms of the fire point temperature wherein a copious amount of liquid comes over here, and in terms of the self ignition. What we do in the next class is we will go further and analyze one or two examples by which we can interpret this phenomenon and identify explosions due to the limits of flammability, and then move into the chapter on detonations. Thank you.